I did not expect so many people this morning, so thank you so much for coming so early. I tried to remember yesterday when did I come for the first time in Dubai, and it was about 13 years ago. There was a room full with 30 very brave men who were waiting for me to come and teach them something new, something that would change the industry. The product was called Revit, and the approach was called BIM. It is obvious to me, now that I see the city and everything that you have built, there is nothing more to teach you about Revit, because you have definitely pushed BIM to a place where I've not seen it anywhere in the world. So thank you for that. Today, I was rather thinking to talk about a little bit, to expand on Linnell's and Uwe's presentation, and talk about these technology innovations that are really impacting the way we will design and make in the future. Because as we all agree, the future is not what it used to be. It's changing all the time. So let's take a look. Let's start with a little observation. Imagine you're in a room where somebody is holding a hammer and a chisel, and is chiseling away a little art piece. And imagine you have never seen in your life a hammer or a chisel. How long do you think you would need to learn how to do this? 10 seconds, 15 seconds? Our brains are as beautiful as that. We see something, we pick it up, and we can do that. Now, before I continue, let's put this on a diagram. I will put the machines or the tools that we make on the lower part, and the humans and the learning that we need to do to learn those tools that we make on the upper part of the screen. So it's a little bit a stretch to call a chisel and a hammer a machine. It's a simple tool that helps us do something. So it does a little bit of something, but we also need to learn a little bit to use it, right? Well, let's go to the next innovation. Now we're talking about a wood lathe. A wood lathe, you know, it can hold a piece of wood or metal, a big chunk of that. It's holding it left and right on an axis. It spins, and you hold a strong piece of a tool that cuts through. You see that, and you say, oh, this thing is just spinning. I can pick it up very quickly. Well, not so fast. If you try it, your tool might get stuck or fly away, and there's splinters, and there is dust everywhere. So you did need to learn a little bit more. The tool became more sophisticated, but you needed to learn a little bit more to use it. Let's go to the next one. This is a Cnc Machine Six Axis. I work in San Francisco. We have a Pier 9 that has a lot of these beautiful machines that can do anything, any shape you imagine, in metal, in styrofoam, in wood, etc. Sadly, I need about 2 weeks training to even get approach to the machine, and then about 2 months or more to learn G-code. So what are we seeing? As the tools become more and more sophisticated and can do more, we need more and more time to learn it. I consider myself smart, and I'm a technologist. And when I see all the tools today that can make this, dynamo, grasshopper, computational design, I love it as an architect. But oh my God, it's not easy to learn, right? So where are we going? The tools are not going to get stupider. They're actually going to be smarter and smarter. But we, as humans, can learn only so much. There is a limit after which we cannot learn anymore. It's just too fast, the pace of change, to catch up with. And my colleague Mike Haley, who is actually leading the AI lab, it's not me, he calls this moment a moment of unsingularity. This is where we humans cannot go further than what our brains allow. So imagine if I need to learn this machine in 2 months, but the machine or the tool changes already within those 2 months, then I can never catch up anymore. So is this disaster waiting to happen? No, and this is where we're excited. This is exactly where machine learning and artificial intelligence comes. Because until now, the tools were doing, and we humans were thinking. Now with artificial intelligence and machine learning, we can offload some of the thinking to the tool, and thus the gap between us and the tools will reduce. And that's why we're excited. So Mike and I were talking about what are kind of the major groups of things that we see that will change with artificial intelligence. And we believe that it will be in these groups. It will help us dissolve the human-machine interface. It will help us learn from the past. I can't tell you how often am I hearing from customers saying, you know, we have no way to learn from previous projects. So we build non-stop new buildings, but every next building is not better than the previous one. There's something wrong about it, right? Then think beyond your brain. We all live in our constrained brains. They're beautiful, they can do a lot of things, but they can only go so far. And make like never before. So today, I'll guide you through the technology trends that actually are all together helping to arrive to artificial intelligence and machine learning. And you will not hear many new things, but maybe I'll try to connect some dots for you. Our lives became digital. From entertainment to communication to medical to bank, everything is online, everything is digitized. And since recently, we managed to also digitize the physical world around us. The first devices were laser scanners. You know how it works. It spins and it shoots laser beams in space. It hits the first surface. It registers the XYZ coordinates, brings it back into the machine, and we have something called the point cloud. These machines used to cost almost $1 million, $600,000-$700,000. Now you can buy the most advanced laser scanner for $60,000-$70,000. That's quite a democratization. Then we have a myriad of new types of scanners. There is Tango, there is Kinect, there is structured light, blue light, white light scanners. All of them help us digitize the physical world around us. And then we have photogrammetry, the process of taking photos, simple 2D photos with your phone, with any camera. And if you took enough photos of an object or of a space, it automatically, through an algorithm on the cloud, converts into a 3D digital model. Now, could you have modeled this statue? Of course you could, but you need to be an expert in Max or Maya. You would need a couple of weeks at least to do it. And it would never be the actual digital copy of the object. It will be an interpretation. This is the actual digital replica of the object that you took. So we started with laser scanning in Autocad a couple of years ago, and it looked like this. It was black and white. It was not understandable, and it was killing AutoCAD. You put it in AutoCAD, and AutoCAD was going like this. It's like, what happened to me? I cannot work anymore, because it was not prepared to consume this type of point cloud and this type of data. That very object, that very scan, looks like this now. Both sensors have become better, but most importantly, the software has become better. And now we have ability to use this, to use laser scanning and photogrammetry to capture either existing spaces, to represent the data in many different formats, to auto-register the scans. All these things that were really a pain to do before are almost a single-click thing. And if all of that was not enough, we live in an age of drones. You can fly a drone without even thinking about it. It follows you like a dog without a leash. In the clouds, and basically we can fly it to capture just about anything. Earlier, we had to remodel everything on the street, all the surrounding buildings, in order to start designing the new building. Well, now we don't have to. I fly 2 rounds of drone capture, and here is what I have. Now, this is my starting point, and from here on, I actually focus on the task at hand and not on reconstructing. Or if I'm in civil engineering, again, I fly the drone. I can calculate how much earth do I need to excavate, how the access points will be for the first trucks, etc. And this is not only interesting for when we plan new buildings, it's also a good way to save our heritage. We're losing our heritage due to terrorist attacks, due to earthquakes, tsunamis, and it will be beautiful for the future generations to keep an archive of what we have. The government of Rajasthan has started to do digitization of all their beautiful, beautiful palaces. And their idea is not only to use this for saving an archive of the future, for the future generations, maybe for future digital tourism, but also as a help to go towards smart cities. In the gallery, you also saw a Baroque topology exhibition. I was also working on this with Professor Saunders, who is actually a professor who teaches Baroque architecture. Now, if you're an architect like me, when you studied architecture, you know that we learned all the complex architecture from floor plans and sections. But Baroque architecture is this beautiful combination of sculpture and painting and architecture, so it's not really understandable if you learn it from just sections and floor plans. So Professor Saunders said, I will try to use all of this technology to teach my students properly to understand Baroque. And that is what that project is about. They picked about 14 most important churches from the Italian Baroque. In Italy, they went with the students, they scanned the churches, and they created these unbelievably beautiful captures of the churches that you can experience online. You can look in detail. We made 3D prints. Now, the 3D prints, this is not the print of the outside of the church. Rather, imagine that you're filling up a church with water, and then you freeze the water, and you break the church, and what remains is this sculpture. So this is actually the positive of the negative space. And they're beautiful. So the idea was that every of the students will take one of those churches to analyze it, but the pattern of all of those churches together, in the future, with machine learning, we can start actually reverse engineer and understand what makes Baroque Baroque, what makes Renaissance Renaissance, et cetera, et cetera. So this is the reason why the digitization of the physical world is important. And you can experience on the website also these churches from inside or outside in a web browser. A couple of years ago, we started a project with the Smithsonian Museums. They're the biggest collection of museums in the world. They have about 154 million objects. And if you're somebody like me who goes to museum, this is what you see, 1%. They simply don't have enough space to put all the artifacts. So they wanted to solve that problem. They wanted to expose everything they have that is hidden in down archives, in the, in underground, etc., and show it to the world. So we started to talk. They not only use digitization technologies, but they needed a tool that will display as beautifully as in real life and not as in Second Life, the digitized objects. And that's what we did. We did this web tool for them in which the objects are gorgeous. And not only you can experience them beautifully, but you can augment them. This relief was not visible on the original statue because it was beaten by time. Once digital, we could deepen the relief, and the curator could, for the first time, actually read the story of Buddha on the digitized version. This was a tool for the curators who spend their entire lives with these objects to tell the story in a 21st century way, a way that kids today learn, because for them museums are this boring archival thing that they will just never go. If you're a teacher and you teach about mammoths, you can say, hey, open the Smithsonian mammoth, tell me, how big is the leg? How long were the horns, etc. So, or you can make some art. Let's make a sticker for a T-shirt, etc. So this is a new way to educate, and these digitization technologies help us do that as well. And the final project we did with the Smithsonian was the digitization of the legendary Apollo 11 that usually is stuck in this plexiglass. It's fragile, people don't want to walk in it or touch it, but it needed to be sent to another exhibit, and the Smithsonian team said, let's make sure we digitize this so that we can have a good replica. And out of this digitization happened this. This is beautiful, this is digitized forever, and in a VR experience, you can actually sit inside and experience it for yourself. And we had actually Michael Collins, who was the third astronaut who stayed in the capsule while the others were walking on the moon, who actually came and put the VR set and saw how we today can experience when he was sitting in the Apollo 11. Now, sensors that enabled us to digitize the real world are smarter than that. They don't only digitize geometry, they can digitize pretty much anything today. And here we're talking about the second trend, which is the Internet of Things and the sensors. And we did this a couple of years ago as a test when it was very early. Nobody was yet talking about IoT. This was our Toronto office. We took every possible sensor that could digitize pretty much anything that is digitizable or trackable, like temperature and motion and humidity and light, etc. And we wanted to give it to the building so that the building starts to be smart, starts to be responsive, starts to give us feedback, starts to be alive. So then we put that in a research project that we call Project Dasher, which is an interactive building performance visualization tool. And here you combine basically the sensor technology with the cloud-based analytics, and it bridges the gap between design and performance. We could here see both historic data as well as the real-time performance data and understand how is our building doing. Was it really well designed? Was it really LEED? Are we really performing the way we should? And how are people using this tool, etc.? We can understand for the first time hot and cold calls and really have an insight into the well-doing of the building. We recently opened an advanced manufacturing facility in Birmingham, and we did the same, but in this case, we have a digital twin of the workshop, and the idea is to track all the machines in a digital twin environment and do live performance of all the robots and everything that we have there. IoT means connectivity. Connectivity in a way that we never had before. You connect the software with hardware, hardware to hardware, people with things. These two things create a lot of data. We digitized geometry, we digitized every single signal, audio, video, voice, motion, humidity. Now we have abundance of data. But data means nothing. It's not an insight, it's just data. It becomes an insight when it's computed and when it's processed. But to process a big amount of data, you need computing power. And that's the third thing. We live in a revolution. It's social, it's cultural, and it's technological, and it's called infinite computing. And it happens because of three things. Number one is the rise of the computing power. Number two is the precipitous fall of the cost of that power. And number three, it is the democratized access that we all have today to that power. Now, if you combine that infinite computing with the cloud, for the first time in our lives, we have an opportunity to apply infinite number of resources, computational resources, to solve some of the growing challenges that we have as architects, as engineers, and as designers. So to put it very simple, I have a design problem or an engineering problem, and I take one computer to solve that problem. The computer will take 10,000 seconds, and it will cost me on the cloud 16 cents. Now with infinite computing, instead of giving my problem to one computer, I can give it to 10,000 computers at the same time, and they will solve the same problem in 1 second for the same amount of money. Being able to apply infinite number of resources to solve problems at no additional cost is the first in human history, and this will change forever anything the way we're doing it today. So how will it change design? Linnell talked yesterday. Until now, we, the designers, were directing the tool. We were very explicitly telling the tool, you do this, you go left, you go right, you make a wall, you make a window. We already have the design in our head, so we're just directing the tool. We were deciding when to run an animation, when to run a simulation to validate the design. So if I designed, for example, this car seat, I model it and then I'm sending it to simulation to check if it works. After 7 hours, it tells me, this zone, the red zone, it will break. So then I redesign, I change, I run again a simulation. Again, it runs for hours, only to receive maybe a little bit a better design, but is it optimal design? No, because I was just trying to fix a little bit and to improve. With infinite computing, what we can do now is instead of sending just one or proposing one design at a time, we propose many designs at a time. And this is what brought us to generative design. Basically, generative design is not a product, although we do have a product now that is called Autodesk Generative Design. It's an approach in which the engineer, the designer, informs the tool of the goals. And the goals should be anything that is measurable. It can be size, it can be weight, it can be strength, it can be cost. Anything that you care for, you just define it as a goal, and then with the power of the computation, the software using often evolutionary patterns found in nature is synthesizing geometry for you. So instead of designing the traditional way in which we use simulation to validate the design, we use simulation to design, to discover design. This is about exploration. This is about creating so many options and variations within the solution space that now is open for the first time beyond our biases, beyond our brain capabilities, and we can now see many options and understand the trade-offs. So what results is not only a design that is optimized, that uses less material, that obviously will cost less, etc., but also a design that we might have never designed ourselves. It's something unexpected, something that augmented our creativity. Now, why is this important? Aside from those things, that it's using less material, that it's optimized, etc. It's important because of human bias. And let me explain that. Imagine you have an I-beam, and there is a conduit, and you need to design something in that red space that attaches the conduit to this I-beam. So now I have this problem, and as a human engineer, I'm thinking how to solve it. So I'm thinking with everything I know about static, about structural qualities, about materials, and I'm thinking of ideas, I sketch, and I arrive to 6, 7 ideas. And I'm very proud of myself. I have a couple of options, they all work. What I'm not aware of is that throughout that process, I've been hit by human biases. There are 188 recorded human biases. And what they are basically biases that we're not even aware of. There is an anchoring bias that basically makes me always love my very first idea I ever had. Whatever ideas I had after that, oh, that first idea was the best one. And I must tell you, I'm an architect. Whenever I sketch something, a new design, it always looks like the first sketch. But was it because of the bias that I don't know? Or was it really because it was the best design? We will never know. There are authority biases. If somebody who is an authority says so, it must be so, I'm not questioning. There is confirmation bias. We incline to like versions or solutions that confirm what we already knew, rather than to challenge us. So all of these things are happening, and we're not even aware of that. So while we're constrained in that world of biases, all those blue dots and many more are actually solutions we don't even think that are possible. And that is exactly what generative design helps us do. Helps us de-bias ourselves, helps us go beyond our brains, and not only to be happy with 8 solutions that we made, or 15, but how about 1,000 or 10,000 solutions? Solutions that I, for the first time, understand also what are the trade-offs to get them. So what are our customers doing with this? We worked with Lightning Motorcycles. They produced the fastest ever motorcycle in the world. And so it happens, it's an electric motorcycle. As they say, when you're a winner, you want to stay a winner. And in this case, you want to be faster. How do you make faster? Well, you reduce weight. There is a swing arm that holds the wheels that has to be really strong because, you see, it goes left, right, it has to hold the speed, it has to hold the wheels. It's a very heavy element. So they saw it as an opportunity to reduce the weight. We applied generative design. In this case, it's actually pure optimization, and this is very important to understand. If you start with a shape already, and you just try to optimize it, to reduce the weight, to reduce the material that you use, that's pure optimization. That's not generative design. And many tools out there that are pure optimization, they sell them as generative design. Generative design is when you start just from the goals and constraints. But bear with me. We worked on this, and here, to your left, you will see the final outcome. It looks very organic, and it uncannily reminds you of a pelvis of a cat or a dog. And it's no wonder. This is what nature does. It always optimizes to use the least material, the least energy for maximal performance. So our object now looks very organic. But again, that was when we started with the design that they had already, and we just optimized the shape and the material. This is real generative design, when we just take the touching points, the connecting points to the rest of the mechanism, and then we start applying our rules, our goals, etc. So here, the algorithms themselves then design, synthesize the geometry within the rules, within the goals that you defined. And every time it generates something, you can go to any of those, and it informs you exactly what are the trade-offs. Oh, this one is lighter, but it's more expensive. Or this one is heavier, but it's faster to produce, et cetera, et cetera. So you can decide as a designer what is more important for you. And this is what we arrived to. Now you can say, that looks really weird. And we're not used to these organic shapes because we are used to man-made geometries, right? So we're very aware of that. And we at research, we also look at how do we not only 3D print these shapes, because at the moment they're only printable, you cannot machine them, so how do we machine them? But also, how can we give additional creativity and liberty to the designer that they take generative as an input and then control the output to look the way they want to. You've heard us talk for a couple of years about Airbus. We actually worked with them for a while. They want to really change the flying to make it more experiential, to make it better for the environment, and obviously to be more affordable for all of us. And to do that, again, weight in an airplane is a very important thing. You have a lighter airplane, you use less fuel, the tickets get cheaper, you basically do not impact the environment that much. So the first very project we did on generative design was with them, and it was this partition wall that I'm sure you have seen on previous AUs. The idea here was this was a solid partition. We used generative design to reduce the weight, and we arrived to a partition that looked like this. This partition is 45% weight reduction, and it uses only 1/3 of the material. And now the interesting thing, we always say we use evolutionary patterns in nature. What does that even mean? We didn't digitize the patterns, we're just getting inspired by them. In this case, we used 2 patterns, one from a mold and another one from bone structure. The mold pattern, basically, it's a slime mold, and how it grows, it puts these roots in space, and when a root finds food, it continues. But when it doesn't find anything, it dies, because nature does not want to use any resources that don't provide anything good. And that is something that we did. And the other one that we used was the bone structure as an inspiration for these algorithms. So you're already flying in an airplane that has this, but now we continued working with Airbus to redefine the frames for the seats. Again, they're super heavy. You've sat on the plane, you know they're solid metal. And in this case, we use generative design to optimize the shape, to reduce the weight, but then when we 3D printed it, we did not use the 3D printed part as a frame for the seat, but we actually used it in a lost wax casting process, and then we casted it out of metal because it was cheaper. So metal 3D printing today is still limited in size, is still limited in cost, but we have an opportunity either to 3D print in metal or print in plastic, use it in lost wax casting process as a negative, and then pour in a traditional casting process the shape. The seat is now this light, and they calculated that if they apply this seat on a fleet of their, I don't remember what was the name, the model of the plane, that would reduce the carbon emissions to 126,000 tons, and that would be like taking 80,000 cars away from the roads. And of course, there is over $200 million savings over 10 years on those planes. So this is not about, oh, implement the technology for the sake of technology. This is real money, these are real benefits. I'll skip this because at the moment we don't have time. Now this is something that is interesting. When we printed the partition, we realized how difficult it is for us, for our brains, to understand if it will fail. But the computer could. So while we could hold it in our hands, we could not hold it in our heads. Our brains are only going so far, and this is why we need the help of the computers. Now, everybody says it's easy to talk about mechanical engineering and about manufacturing and parts with generative design. What about architecture? Both Uwe and Linnell mentioned our first project. We tested it on our own selves. We were moving to a new building in Toronto, and we wanted to see if we can implement generative design approach of defining goals and constraints to make for an optimal work environment. And that's exactly what we did. We first surveyed all our colleagues. Oh, I want to sit next to the kitchen. I want to have a view. Oh, I want in a dark corner. I want to be in a corridor because I want people to talk to me. Everybody expressed what is their perfect working environment. And then we, after defining those goals, we evaluated the survey against the hard constraints of the building because the building was already created. We were just talking about the interior. And these are the goals. Remember, goals always have to be measurable. That is the only thing that you will need. So we defined the goals, and we let the system go. This is the power of automation. The tool generated, evaluated, evolved, and explored thousands of options. Just imagine, I was an architect, I was designing houses. You have a family of 4, I design for you. You tell me, oh, my daughter wants this, my son wants this. It's already complicated to think of 4 people, let alone of 300 people with so many different desires and constraints. We cannot do that. We can wing it, but we cannot scientifically do that. With generative design, we will be able to do that. So we got options. We picked one that looked to us like it has the best trade-offs. And today our colleagues work in the office. They're very happy. And we will follow up, and next year we will tell you how they feel and what's happening when new people come and how the algorithm gets adjusted. Now, with generative design, we create shapes that are almost not possible to do with traditional machining. And this is where additive manufacturing comes. This is the next trend, where basically we call it additive because we only add material. I don't need to teach you 3D printing. You're one of the most advanced place about this. But there are some aspects of 3D printing that many people have not realized. So the first is, yes, it uses only as much material as it needs. Great. That's the first thing. The second thing is a 3D printer does not care if something is a straight box or a super complicated organic shape, because the printer just goes left, right, up, and down, and it prints whatever digital file it follows. This can bring ornamentalism back. In design, in architecture, we were avoiding these shapes. We were avoiding to be creative because we were complying to the tools instead of the tools complying to us. So for the first time, we have an absolute creativity and freedom to do whatever we want. When we started with 3D printing, there were only so many materials that we could print with. Today, there are over 100 types of materials that you can print with, and in my opinion, the biggest innovation in additive manufacturing and printing will be new types of materials. Now, if a printer prints by dropping a droplet on every little spot, that means that you can design objects that have, in the same material, different densities, different transparencies, different performances. That's awesome. But we don't know how to design for that today because we design the whole shape. We don't design every voxel, right? Another thing is that if you design this in Inventor or in Fusion and it's a mechanism that works, when you print it in one go. This is made out of 20 parts. They were not separately printed and put together. This was printed as a mechanism. What does this mean for assembly line in the future? What does this mean for manufacturing? This will definitely dramatically impact everything. So if all of this is so important, what are we at Autodesk doing about 3D printing? So we have a set of tools called NetFab line of product, where we not only prepare designs for printing, where you can say, oh, I need this to be, first the geometry to be prepared, but also to make it hollow, because sometimes it's cheaper, you want it lighter, or to do smart nesting while you're printing, or to do simulation. Many prints, especially metal printing, is very, very expensive. I better simulate and see if my print will fail before I spend $20,000 on something that it will fail. All of these are part of the tools. But in research, we also experiment, how do we start designing in a voxel environment so that every voxel can be, one is a rubbery material, one is hard material, one is transparent, one is, because the printer can do that. We just don't know how to design. Imagine I'm designing, I broke my arm, and I'm designing a little, how do you say, protection. So I would like that to be flexible here because I'm moving. I would like it to be hard where I broke my arm, etc. Today, these things are very difficult to design. So in research, we look at that so that we can design objects like this that have different density, different colors, different transparency, that have non-linear, non-uniform behavior, so that you can design beautiful things like this and print in one go something that is already designed within. Printers today print small things, they print slow, and they print expensive. And we want big, we want fast, and we want cheap. So we do a lot of research also on, can we use collaborative fabrication, collaborative printing, where multiple heads are printing at the same time so that we can print big objects. Lots of these things that I'm showing you is Autodesk research. Some of that we will continue. Some of that we're experimenting and validating if it's a good idea or not. This was one of those just to see where can it go, because as you know, in AEC world, we will need large scale if we want to move to 3D printing. Now, this is one of the more and more interesting things about additive manufacturing. I have a colleague, his name is Massimiliano Morizza. He's one of the smartest guys that I have ever met. He believes that we should not be using aluminum or steel or concrete. It's bad materials. And he believes in composites. There are a lot of composites that we can build today that have much better performance and that are not bad for the environment. He developed for Livrea, helped them 3D print entire yacht. And it was printed out of polymer composites, and it was printed in one go without supports with a robotic 3D printing arm. So bigger the scale, the 3D printers become more and more robotic. This is, by the way, from last week. I just edited this slide because this is definitely the largest 3D print ever done. It's a blade mold, wind turbine blade mold, and it's done by Desktop Metal. It's a metal 3D printing company. In the world of architecture, Professor Koshinevitz, more than 15 years ago, talked about contour crafting or 3D printing for buildings on planet Earth or on Mars. His students a couple of years ago in China did the first low-cost housing that were $5,000 per house, and they were printed in 10 hours. This is not bad. Of course, it's not fine, it's still very rough, but you can finish it, etc. But this is going. We are going in that direction. It's just getting better. And we're seeing now a lot of robotic and 3D printing companies trying to do large-scale building printing. APRI says we print buildings, and they're all more on the robotic side because of the sheer scale of the buildings. But the principle is the same. You have a nozzle, you have a material, it goes left and right and deposits the material. So I mentioned the magic word robot, and we cannot imagine any future without robots. So that brings me to the next one. Now, how many of you know where the word robot comes from? Anybody? Yes?
I think it's in the play, it's a robot, that means a servant or something, in the Roman or something.
You're very right. So, Karel Čapek, who is a Czech writer, wrote a play called RUR, and there for the first time uses the word robot. Actually, in my language, rabota is work, but a robotnik is a slave. So don't forget, we created robots to be our slaves. And we should not be worried that they take our jobs. We should be worried that human beings spend their entire life doing work that can be done by a machine. Because none of us does that, but it's not pretty. So, when we talk about robots, when we try to imitate a robot, we do this. What does that mean? Constrained movement. When we say somebody speaks like a robot, what does it mean? It's somebody who is not very emotional, who is just automatically repeating something. So it's constrained, it's repeating, it's non-emotional, not understanding the context. That's exactly the problem with robots today. Robots have been so overly optimized for Six Sigma that they today are completely inflexible. Not only that they have no idea of the environment, but they have been hard-coded to do one particular thing. So this is a very big problem, because if I want to change the robot to do something slightly different, I have to reprogram it. And that usually is done by specialists. So imagine you have a car or any object, and customer feedback is that something does not work well, and you want to improve that product. Well, to do that, you have to stop all the robots, recode them, and then only start a new production line. Nobody can afford that, and that's why companies, even when they know that they can improve on a product, they don't do it, because this is the bottleneck, reprogramming the robots. And also, robots have no idea of the environment. That's why we keep them in a cage, because if you just get close to a robot, he doesn't know that you're there, he can hit you, etc. So these are the things that we're looking at in Autodesk, because many people are asking, why are you even talking about robots? What is Autodesk doing with robots? So let me try to explain what we're trying to do. We're trying to do two things. Number one is, can we develop a better way to talk to the robots, to coach the robots, to interact with robots, so that many more of us, and not just these rare specialists that we depend on, can make them do something. So we started very early experiments where just with a normal movement of my hand, I can make the hand of the robot move. Well, that's easy, right? You don't need to train anybody to do that. We had actually, we call her Madeline the robot Tamer, and she was an artist in residence or engineer in residence in our Pier 9 facility, and she was just doing wonders. You really forget that it's a robot. You think it's an animal next to her, responding. But it's really about how do we create a natural language to interact with them. So our first project, I believe Linnell mentioned a little bit about this. This is our first robot that we worked with. It's the robot called Ash. And we wanted Ash to become a 3D printer, because as 3D printers are limited, we wanted Ash to print that beautiful chair that we designed generatively, but large scale. So we equipped Ash with a MIG welder, so it became kind of a robot welder, and it can deposit molten lava, and it prints like a printer. We gave Ash eyes to observe what's happening, and actually it has a laser. And why is that important? Well, every time it deposits a layer, the laser passes around and it looks at the deposited layer. And if it sees that there was a mistake, then it recalculates how to continue to print in order to get to the object that you really wanted. And it can learn back from that closed loop of information and improve continuously and continuously. So the robot learned how to print and learned how to teach itself to print better. And here is the chair. We did something else with Ash. We wanted to enter into the world of Ash. We wanted to control it. So we created a full-scale virtual environment where we, with the joystick of the VR set, could actually control it. Why? Well, first, when we plan some activity, this is easy to see if it will hit something, how far it needs to go, etc. You can see how it's totally easy. And that is really how we think that we might be able to teach robots in the future and experiment more intuitively with them. We did something further for the last AU. Actually, we created a robot, a virtual robot that can actually recognize curtain wall panels and guide it to install them on a construction site. Now, you understand tall buildings better than anybody else. You don't want to be the worker who is on that 150th floor installing curtain walls. It's dangerous and it's inhumane when you think about the temperatures or the weather conditions. So we can, today, through VR sets, actually control the robot and do this. But in the future, we hope that through the human interaction through the VR sets, we are gathering data that we can then train a machine learning system, and the robot can do it itself, and you're in the office and you just control if it does it well. And I said the magic word, through machine learning system. What does that mean? Machine learning is really the science of getting computers to act without being programmed, okay? All they need is a bunch of data. We feed a bunch of data to a neural network, and it starts to look at patterns through the data and starts to learn things. That means for the first time, we can do machines do complicated things without needing to program them. Machine learning is happening already. You're all users of machine learning tools. If you are using Netflix and have movies recommended, that's machine learning. If you're writing in Google and you have autocomplete of a sentence, that's machine learning. Natural language processing, when you talk to Siri, that's machine learning. So we're already exposed. And obviously the most advanced form of machine learning that we know is the self-driving car. The self-driving car feeds from the information that it gets on the street, and thanks to that information, it predicts what to do next. If we had to code, to program a self-driving car, it would have been impossible. Because think about it, I would have had to program every possible condition for driving. How is that even possible? I have to program every possible situation in which somebody comes from left, from right, a dog passes, it rains, the car in front of me skids. There is no human brain. You cannot put as many developers that you want to put. They will not be able to code this. The only way to do this is through machine learning. And that is what we're doing. So we said, how is it possible that kids can in 5 minutes learn how to assemble Lego bricks? Can we teach a robot to do that? Can we have a robot learn how to assemble Lego bricks? So we took another robot. This is a smaller robot that we call Bishop. And we introduced Bishop to the disorderly world of Legos. We wanted Bishop to recognize Lego bricks and assemble them. And to do that, we equipped Bishop with a camera and with an accentuator. So Bishop understood that it has eyes to see and hand to grasp. And after a couple of data feeding through machine learning system, it kind of understood how to find a brick, catch it, and put it. And we were very impressed. But Bishop was learning very slow. So we had a choice, either to buy thousands of Bishops and all of them learn and then gather that experience and learn some bigger truth, or to say, we will actually create a simulated virtual environment for Bishop in which we will basically replace what he sees in physical world with simulated bricks and then do all the learning in a simulated environment. By decoupling the learning environment from the physical world, we decoupled time. Now, the robot was learning in computer time. We left him one night, and in one night, it already understood not just to pick however, but to reorient itself and then pick on the best position of the brick. That's amazing. Can you just believe that all of this, you would not have even been possible to code, and it just coded itself in a couple of nights? That's crazy. These are all the simulations that it did in just one night. So here is Bishop now. He's much faster. And what's important here is, it's not like the previous robots where the bin has to be here and they have to drop here. If the bin moves a little bit, the robot is confused because he's only hard-coded to take from here to here. With Bishop, if I push the brick somewhere else, he doesn't care because he knows wherever is a brick, I'll find it, and wherever is the plate, I'll put it. That is the big difference. This is for the first time we will allow robots to be able to respond to change. So that today, if I want to change my design, I can just feed the robot the new digital file overnight, it will figure out, and then in the morning it continues the production line with the new model. And imagine when one robot learns, all the robots have learned, because we can transfer that knowledge to any machine. This is huge. When we talk about push-button manufacturing, when we talk about lights on 24-hour factory, this is what we mean. And this is why Autodesk is working on this, so that we can then, from the machine learning data that we get from the assembly of the objects, etc., feed back that information, that knowledge to design. Because when you design today, you don't necessarily think of the things, how something will be assembled. You think of your design, and then some engineers are figuring that out. Well, maybe if we do in the future quality assurance or assembly with robots, and we know that, for example, a shininess is a problem because the robot is using computer vision to assemble or to do quality assurance, then maybe I will, in the design phase, think, do I really need this to be shiny or not? So we're informing design with assembly and quality assurance back. Now we have one tool that we already have and customers are using in a beta, where we applied fully machine learning. Learning from the cars that take all the information from the environment and feed a predictive information, we said, can we do that, the same thing for construction? And majority of you are from the industry. I don't need to tell you, we know it's high risk, low margin industry. So any help is a great help. So we were looking at all the types of data that today on advanced construction sites, the workers are being able to capture and input in the products that they're tracking the progress with. So we created something called BIM 360 IQ. We realized that there were 24 million reported issues on BIM field, and we said, what if we could learn from this data? So we contacted customers, and about 40 now construction companies from all around the world are participating. They're sharing all their data with us, and out of that data, we managed to create a system that, according to them now, works about 98% accuracy and can predict risks on a construction site. So imagine you're a superintendent, you come in the morning and you open and you see you have about 300 issues. You can drill deeper down in any of the issue, and you can see, okay, concrete issues or water issues, etc., and you can assess. But the system classifies the information from previous historical knowledge and knows that water issue, for example, is a big thing, so it will burst it up. Now, because we're still working on this, sometimes it doesn't predict correctly, so then we have opportunity to amend and fix what was proposed and say, this was not a water issue, it was something else. But this works like a charm, and it has 5-6 machine learning filters through which the information goes. But this is learning from past. This is learning from the past experiences. We crawl the data, we correlate different types of data, and we are able to predict. And if you are an owner who has multiple projects, like in this case 32 projects, you can see all of their projects, the state of the risk in those projects, are they delayed, etc., and then drill deeper down like the superintendent and start from zero. On a construction site, you also have, on big sites, 200, 300 subcontractors. Wouldn't you also want to know how are the subcontractors doing? You can every day tell if who of the subcontractors is delayed, who has issues, but you can also historically keep track of which subcontractors generally performed well or not. At the moment, we're doing this with pure text input on BIM field data, but we are augmenting this with any other types of inputs, with photos and videos, and any other information that can help correlate the data and bring an insight. So for example, if we use computer vision, we can say, oh, there is a darker spot in front of the window. That must be water. And then we immediately can do a real-time alert. There is a water issue. It brings it in BIM 360 IQ, and the superintendent knows how to deal with it. And we can do risk assessment also on the safety. If this is a very tall building, these workers are there, but there is no railing, the system will notify that. And Uwe showed some of our partners that are on Forge developing solutions for this. One is Smart Video. It runs video on site, real-time, classifies the data through machine learning, and then analyzes real-time through machine learning what's going on. In this case, it looks at the humans and checks if they're in safe conditions. We also have Forge partners like Connect Tech, who are basically allowing you to access the current BIM data on-site directly. They're doing that through AR/VR environment. At the moment, they're manually adding data, but we can actually, with automation, machine learning, real-time add the data. So for example, you can see through XR to mixed reality, oh, this bolt is missing, that's a safety issue, there is a mold here, etc., etc. When it comes to machine learning, we actually started a long time ago. We created something called Design Graph. We kept on hearing from our customers, we never learn from our past experiences, we never learn from our past projects, we cannot find any data, it's stuck in different file formats, it's labeled wrongly, it's texted wrongly, etc. So we created something called Design Graph, where it was a new way to explore all your data across all your projects, provided they were on one place. It's a shape-based search that understands the shape, but also the topology, and it enables you to understand how are your projects constructed. So this is the whole graph of your projects. At the moment, there are hundreds of projects. It visualizes every project, and it visualizes all the parts in that project and all the sub-parts in that project. Imagine that in your world, basically having a knowledge of graph that finds every of your buildings with every of the components used in those buildings. In a very, very early research phase, this looked like this. Here are all my projects. I pick one. It shows me immediately all the parts that I have, and I see them visually. But if I pick one of the parts, then it tells me where was that part used in which projects. So it can go, you start with a part and then finds it across all projects, or the opposite way. So then in the next stage we said, either through search or in a design phase, you have an object and you say find similar. So this is smart search, this is find similar in manufacturing. If you design twice something, you're ordering it twice, but it was probably the same object. We can find duplicates or almost similar duplicates. But just smart search is just the beginning. Where this is going is predictive, assistive, autocomplete for design. So that then, one day when you design something, it says, oh, you're designing this? Well, this usually goes with a bolt. Oh, and if you use bolt and this, you're probably designing a bicycle. And it completely reconstructs the tools that it offers you because it understood from the parts which subsystems you can build, and from the subsystems, what are you actually building? And when you look at these components, these lines that connect them, that is the knowledge, that is the graph. This is what I call X-formation. This is where we lost the information. How did we arrive to this? It's not captured anywhere. But the machine learning system finds the patterns, finds the relationships, and basically creates ontology of what makes a chair, what makes a building. So to finish, I'll finish with creativity. Where is this all going? We're hearing of computer-generated music, computer-generated pictures. So a couple of years ago, there was a company, NQ, who created a fully artificial intelligence-made movie. Basically, the artificial intelligence system created the script and directed the movie. It was only real actors that were acting. The movie was intense, hilarious, and absolutely unwatchable. I do recommend that you watch it. It's on YouTube. It's called Sunspring. While we're always joking about that one, there is something that we don't joke about. And it's a project that you absolutely have to Google. It's called the Next Rembrandt. And it was the most beautiful merging of creativity and technology that I've seen. So scientists from the Walter Thompson Institute in Netherlands decided to teach a computer to paint a Rembrandt. They fed the computer about 350 paintings done by Rembrandt that were digitized. And then they defined the goal. I want to paint a male that will be 30 years old, that will have a little bit of facial hair, that will have a hat, etc. They need 9 months to feed information and the pattern to start understanding, Rembrandt was always painting the eyes like this, with a distance like that. When he was doing the cheeks, he was doing this. And then in painting, we don't understand, but painting has a third dimension. When they want to emphasize something, the painters are adding more paint, etc. The system managed to generate and to 3D print a Rembrandt painting. 347 years after Rembrandt died, there is a new Rembrandt that a curator could not tell was not painted by Rembrandt. I invite you to watch it. It's on YouTube. Just write the Next Rembrandt. It is the most exciting thing I have seen. And this is what will happen with design as well. I have one video that is rather a provocation. It's not serving as inspiration. It might make angry. It might make you uncomfortable. But parts of that we do believe that will happen. I need the audio for this. I hope it will work.
Autodesk, I want to design a chair.
Here are some popular chairs. Scroll through them and select some examples to give me an idea of the type of chair you would like.
Okay, I'm making some selections now.
Just think about all the technology that is hidden behind
Here are my
this.
picks.
All right, here are the chairs you selected.
Okay, combine all possible pairs between these 6.
All right, there are 15 possible pairs. I am morphing the form between all pairs, generating a large range of combinations. Here are 5 design possibilities between each of the 15 pairs. There are a total of 75 possible designs.
Okay, great. That's a lot of options. Let's go back to my original selections and I'll just direct you step by step.
Okay, here are your original selections.
Okay, combine these 2.
All right, here are 11 options between the pair you selected. There are 2 repeated sets to show both original leg styles. Scroll through them and select one to make further design changes.
This one looks good.
All right, here it is.
Show me the other leg options with this chair.
Do you know how many times have I modeled
Here are the
legs?
6
Why
original
would we
leg
need to
styles
model
adapted
them
to this
every time,
design.
right?
Select any style you would like to use.
Okay, switch to this one.
Okay.
Make it wider?
Okay.
Not that much. Split the difference.
Reducing width 50%.
Make it work for a really tall person.
Like
All right.
Airbus.
Lower the top of the back to this red line I'm drawing.
Okay. Here you go.
Okay, make it into a lounge chair.
All right. Matching to the parameters of a known lounge chair with high user ratings for comfort.
Show me a comparison of the two.
Here you go.
Make the chair look good inside this space.
Adjusting materials to fit in with the environment you uploaded.
All right, make the materials look like this outfit.
All right. Here it is.
Nice. Save that version.
Okay. Version saved.
Show me 5 visually similar patterns to this dress.
Okay. Here you go.
Zoom into this one.
All right. Here it is.
Show me this one.
Okay.
Okay, save those two.
All right. 2 versions saved.
You get the idea, right? I watched the documentary of Miroslav Grčić. He is one designer that I like a lot. It was on United. This is exactly how he talked to his human assistant. After the initial design, this is how senior architects in the firms that I was were working on. They were like, can you make that? No, make it like this. You know, that's how we want to work. Instead of holding a mouse and for 300th time in our lives designing the same leg for the chair, etc. So while the beginning might have made some people uncomfortable, wait a second, I'm a designer, you're telling me that I'm just going to be a picker now. This can be really the future of personalized design, when a company that creates chairs tells you, oh, you can design your own chair and we're making it. But for a designer, I can start also with a sketch that gets automatically converted into 3D because we're close to be able to do that, and then continue. All the repetitive stuff, all the drudgery, all the things that you never needed to do, but somebody can do it for you. I hope you saw that from all of this, data was what was driving all of that. And Andrew Ng, who is the legend of machine learning and who's making all the courses, a professor, he said actually last year, data is the new electricity. We say data is the new fuel. It will be what people will be fighting over. It will be what people will be charging for. And it will be, on a serious note, what will help us make much more informed decisions and not just understand how well we did something, but how can we predictively, how can it help us, assist us to make things better in the future. And with machine learning, data becomes an insight, data becomes knowledge. And hopefully you saw through all of these things that if you see on the left side, and that was the old tools of the past where we were directive, they were rigid, they were inspectable, they were conditional, they were conform. We are now having a relationship with our tools that is much more adaptive, that is fluid. We have tools that start to understand us and start to behave like this overly ready to help assistants that know everything, remember everything, and help you do the best. So it's not about us or the machines, it's humans and machines that will power the future. Thank you so much.